In today's class, we are discussing thermochemistry. And what is thermochemistry? Thermochemistry is simply application of thermodynamics to chemical reactions. So, in this topic, we are going to learn study of heat changes happening in chemical reactions. So, what does it mean? It is basically application of first law of thermodynamics. Application of first law of thermodynamics. Law of thermodynamics. Can I write TD thermodynamics to chemical reactions? Chemical reactions. So in any chemical reaction, basically two things happen. What are they? So breaking of bonds in reactants, and finally the making of bonds to form products. So this happens in reactants, and this step happens to form the products. So these are the two things that happen in any chemical reaction. So breaking of bonds associated with uh, involvement of energy is required to break the bond. When the bonds form, the energy will be released. So here, when the energy required to break the bonds is higher than energy released when the bonds are formed to make the products, that reaction is going to be endothermic reaction. Why? Overall energy is taken more than the energy released. Therefore, it is a endothermic. In opposite, if less amount of energy is taken to break the bond and the greater amount of heat is released when the new bonds are forming to give the products, those reactions are known as exothermic reactions. So we have exothermic reactions, endothermic reaction. Endothermic reactions involve absorption of heat, and exothermic reactions are associated with release of heat. So we can say in exothermic reactions, heat is product. So exothermic reactions, the heat is a product. Heat is a product. And in endothermic reactions, heat is a reactant. Heat is a reactant. So what is thermochemistry now? Energy changes involving in chemical reactions, and we learned that energy and reactions are two types in terms of energy factor, that is endothermic reactions, exothermic reactions. So endothermic reactions are basically uh, represented with their enthalpy delta H as negative for exothermic reactions, and for endothermic reactions delta H is positive. So here in endothermic reactions, enthalpy of the products is greater than enthalpy of reactants, and in exothermic reactions, enthalpy of products is smaller than the enthalpy of the reactants. We will study what is the enthalpy of reactants and products. Basically, we are going to assign something called enthalpy to each substance. So there is going to be some terms which is called enthalpy of formation, enthalpy of reaction, enthalpy of combustion. All those things we study in detail. Now, chemical reactions generally expressed with using two conventions: chemical reactions happening at constant volume and chemical reactions happening at constant pressure. So let's talk about chemical reactions at constant value. At constant value. So as the reactions are happening at the constant volume in the process, delta V is equal to 0. That indicates W, the work is negative P external times delta V is equal to 0 in the reaction. So therefore, what if we apply the first law of thermodynamics, that is delta E is equal to Q plus W. So that's going to be delta E, and we are supplying heat at constant volume, therefore we can represent that as QV, and work is 0. Therefore, whatever the heat supplied or whatever the heat lost, everything is happening uh, uh, from the internal energy point of view. So if the heat is gained, that results in the increase of internal energy. If the heat is lost by the system, that results from the loss of internal energy to the system. Therefore, the QV is equal to delta E, which is E2 minus E1. And E2 minus E1 are absolute internal energy values, which are difficult to determine. We already know that absolute internal energies, absolute enthalpies are difficult to find out. In chemical reactions or processes, we always study change in enthalpy and change in internal energy. Okay, and as we are using a chemical reactions, let's say E2 as the energy, internal energy of the products minus internal energy of the reactants. So this is the that's equal to QV. So this is the expression for chemical reactions at constant volume, the energy changes or heat changes involving in that. Now another one, the most common one in chemical reactions is chemical reactions at constant pressure. So most reactions are performed in that fashion where reactions happen at constant pressure. We don't change the pressure, we allow the volume to change, but we don't do other way around. So now we are dealing chemical reactions at constant value, sorry, constant pressure. So here volume changes are happening, therefore there is no uh, point that there is no work done. Definitely here there is going to be some work. So therefore, so here there is a work, there is change in internal energy, and there is also heat transaction between the system and surroundings. Therefore, whatever the heat we supply, definitely involving in all kinds of changes. Therefore, if we apply the first law of thermodynamics, that is delta E equal to Q plus delta V, sorry, P delta V. And P delta V, what is, sorry, I made a mistake. What is the expression for the work? Negative P delta V. So if we substitute here, the heat we are supplying at constant pressure minus, for the work it is minus P delta V. And therefore QP, we can write delta E plus P delta V. So that means here QP, so delta E plus P delta V is known as delta H. So for chemical reactions we can say that QP is equal to delta H is equal to H2 minus H1. So the heat changes are happening at the cost of enthalpy of uh, the species involving in the process. So heat of reaction at constant pressure is equal to change in enthalpy. Now what this enthalpy and internal energies uh, in a schematic presentation for endothermic and exothermic reactions. In endothermic reactions, energy is absorbed. So that means reactants enthalpy is less than the product's enthalpy. Now let's write for energy profile diagram of endothermic reactions. So on the x-axis we take energy, the y, on the y-axis we take the energy, on the x-axis we take the reaction coordinate. So now here we have reactants, corresponding to this energy, and this is kinetic factor, activation energy. Now these are the products, and this is the gap between the products and reactants energy. So this is known as a delta H, which is positive. So this much energy is more for reactants compared to uh, for products come with respect to reactants. What happens for exothermic reactions? In the exothermic reactions, we have enthalpy of the products is less than enthalpy of reactants. This is reaction coordinate. So the reactants have greater enthalpy or internal energy. These are products. And this is delta H for this exothermic reaction, which is negative, and here it is positive. And this is reactions expressed at constant pressure. If we express that at constant volume, this is going to be delta E, and this is going to be delta here, which is negative for exothermic, and this is positive for endothermic reactions. So are they equal or different? The energy changes involved in a chemical reaction, let's say for a same reaction which is happening at constant volume, in another case which is happening at constant pressure, are they equal or different? Let's study. So now we are going to make a relationship between QV and QP. A relationship between QV and QP. Essentially, it is a relationship between delta E and delta H for chemical reactions. And we know that QV is equal to delta E, and we know QP is equal to delta H. So therefore, what is the relation? We know QP, which is delta H, is equal to delta E plus P delta V. Or in simple, let's say this is happening at constant pressure. Therefore, whatever the volume changes are happening, those changes essentially coming because of the change in temperature and change in number of moles. Let's say the reaction is happening at the constant temperature. So therefore, the volume change is basically associated with only change in number of moles. Change in number of moles. So value definitely going to change for the gases. For the solids and liquids, the change in volume is almost negligible. Therefore, if the reactants and products both are volumes and liquids, both are liquids and solids, the delta V, that is change in volume, is almost zero, that is negligible. But when the reactants and products are gases, the change in number of moles will result in a significant change in the value. Therefore, there will be a significant delta V. That means P delta V is equal to delta nRT. Why here? The P is constant and we are also taking the temperature constant. Therefore, volume changes are basically related to change in number of moles. And what kind of moles here? Involving gas moles. Why? That when the substances like solids and liquids involved in the process, there will be no change in the volume in the reaction, but the gases are involved, the changes are very significant. Therefore, we can write that P delta V as delta nRT. Now from this we can say QP is equal to QV plus delta nRT. That means delta H is equal to delta E plus RT delta N. This is the relationship between heat of reactions at constant volume and heat of reaction at constant pressure. So that is delta H equal to delta E plus RT delta N. Now let's take the examples. So first one, NH3 gas, 2 moles decomposing to form 1 mole nitrogen gas plus 3 mole hydrogen gas. So here reactants and products both are gases. And what are the gaseous products here? There are 4 moles of gases, 1 mole nitrogen and 3 mole hydrogen. Therefore 4 moles of gas products and 2 moles of gaseous reactants. Therefore, sorry, so that is going to be NR. NR is equal to 2. So from this we can say delta N is equal to products moles, gaseous products moles minus number of moles of gaseous reactants. That's going to be 4 minus 2 is equal to 2. So for this reaction, delta H is equal to delta E plus delta nRT. What is the delta N? 2RT. So for this reaction, delta H is greater than delta E. Next, another example. Let's take the second example, that is 2H2 gas plus O2 gas is giving 2H2O gas. So here the reactants are gases and products are gases. How many gaseous products are there? 2 moles are there. Now how many gaseous moles of reactants are there? There are 3 moles of gaseous reactants. Therefore change in number of gas moles is equal to 2 minus 3, which is equal to -1. So here delta H is equal to delta E minus RT. So we can say that in this case delta H is smaller than delta E. And let's take another one, calcium carbonate solid decomposing to calcium oxide solid plus carbon dioxide gas. On the left side, that is reactant side, there are no gases, the volume is very less, and which is decomposing to give you solid, which occupies very little volume, but there is a release of gas which is going to take significant volume, because when we have a gas, the particles are far from each other, therefore they tend to occupy whatever the volume available to them. Therefore here number of gaseous products are 1 and number of gaseous reactants are essentially 0. Why? The volume, the significant volume is basically is associated with the gases. When we have a solids, the changes in volumes is almost negligible. Therefore when we are making a relationship between delta H and delta E, we don't consider solids and liquids. Therefore what is the delta N for this reaction, which is 1 minus 0, which is equal to 1. Therefore delta H is equal to delta E plus delta N is 1 times RT. So in this case also delta H is greater than delta E. So if the gaseous products of moles of gaseous products are greater than number of moles of gaseous reactants, for those reactions delta H is greater than delta E. In other way, when we have gaseous reactants in greater moles compared to gaseous products, in that case delta E is greater than delta H. For those reactions which completely involve only liquids and solids, there is no involvement of gases, for those reactions delta H and delta E, they're almost same. There is no significant changes in their numerical value, so they are almost equal. Now let's go to thermochemical reactions. What are thermochemical? We know chemical reaction. What is chemical reaction? A chemical reaction is the one that is associated with the formation of the new substance, and in scientific terms we express that using an equation. We write on the left side reactants and change is shown with arrow, and right side we write products. And when we have a reactants, we write them on the left side using the plus addition symbol. Products also, if we have more than one, we write them using the plus side. Now, what is the thermochemical equation? A thermochemical equation is the one that we write for the balanced chemical reactions indicating their physical state plus the heat involved in that reaction on the reaction right side exclusively. Let's say, for example, we have a balanced equation like this one: C graphite and oxygen. So what are we doing here? We are expressing the reactants using their physical states, and we are also expressing the product using its physical state. And the heat enthalpy of this reaction we are writing on the right side of, that means exclusively uh, outside of the reaction balanced equation, that is delta H. Let's say at 298, that's going to be negative 393.5 kilojoules. This is known as a representation of thermochemical equations. What is thermochemical equation? A thermochemical equation is a balanced chemical equation that indicates physical state of each species in the reaction beside, just beside their formula within the brackets, and delta H for constant pressure reactions and delta E for the constant volume reactions on the product side separately. So now we are writing thermochemical equation. So that has essentially a balanced chemical equation. And what is the other point we have? So each species physical state is mentioned in the bracket, and heat of reaction, that is delta H and delta E, are denoted separately on the right side. So now this one, each species physical state is mentioned. How we mention? The gas is mentioned using symbol G in the bracket. Liquid is mentioned using L in the bracket. Solid is mentioned using the L in the S in the bracket. But if it is a substance dissolved in any solvent like water, let's say a substance dissolved in water, how do we express that? Beside that substance we write AQ. So let's take an example: HCl aqueous plus NaOH aqueous. What does it mean? HCl in water, NaOH dissolved in water, that is giving us NaCl aqueous plus H2O liquid. This is how we write a chemical equation. Along with, we mention each species physical state, and outside of that we write energy changes for that reaction, that is going to be negative 57.32 kilojoules. This is how we represent the thermochemical equations. Every reaction must be expressed like this. Now, enthalpy of reactions. So heat of reaction. heat of reactions. So heat of reaction, the energy changes involved in the reaction can come from internal energy and the PV term. So if the reactions are done at constant volume, those are expressed, heat of reaction is expressed with delta E, and if the heat of reaction is expressed at constant pressure, we use delta H. So therefore, in a more general way, heat of reaction generally expressed as enthalpy of reaction. More or less same. Only difference is heat of reaction is related to both terms, delta H, which is heat of reaction at constant pressure, and delta E, heat of reaction at constant value. But more generally, we use a constant pressure reactions. Therefore, the heat of reaction for the constant pressure reaction is basically enthalpy of reactions. Therefore, now from this point onwards, we exclusively write enthalpy of reaction, and that must be understood as heat of reactions. So now we are going to learn enthalpy of a reaction. What is enthalpy of a reaction? Enthalpy of a reaction is defined as enthalpy changes associated when reactants are becoming products. The enthalpy changes associated with a chemical reaction is known as enthalpy of that reactions. So therefore, delta H of reaction, so I can say this one reaction, I write Rxn, which is the enthalpy of the products, summation of enthalpy of products minus summation of enthalpy of reactants. This is the formula for enthalpy of reactions. Okay, so here it says H absolute enthalpy values of products, absolute enthalpy values of reactants. But we know for enthalpy, difficult to determine absolute values, difficult to determine absolute enthalpy values. Absolute enthalpy values. Now this is a problem. Therefore, we need some kind of a reference point, arbitrary selection or arbitrary assignment of enthalpy values to some substances. From those arbitrary values, we can able to give some kind of numbers to enthalpies to remaining compounds. For that, we need to define a state for some substances, for all substances, and we need to assign some enthalpy number to the substances at that state. So for that purpose, there is something called standard state was taken as a arbitrary selection. So standard state. And this state was selected arbitrarily, and which is a reference point. And for this, and what is arbitrary value assigned for standard state? And basically elements were elements in their stable form, the stable form word is very important. Stable form at 298 Kelvin, that means 25 degrees centigrade, and 1 atmospheric pressure is taken as standard state, and the enthalpy assigned to the elements when they are in their stable form at this temperature of 298 Kelvin and 1 atmosphere is 0. So what was the assigned value for all elements? Standard state, that means standard enthalpy of formation. So how they are formed, so formation enthalpy, so that is HF naught. uh, is taken as 0 at standard state. So this sign naught denotes the standard state, that is 1 atmosphere pressure, 298 Kelvin, and some modern books use the pressure as 1 bar. Now if element is not its standard state, then its enthalpy is not equal to 0. Then how do we find its enthalpy? The energy associated in bringing that substance from standard state to the state of where we are interested, that energy associated is known as a enthalpy of formation for that element at that condition, at that state. Okay, so therefore enthalpy of formation for the elements at standard state was taken as 0. Now let's go to what is standard state. We already defined for an element in its stable form at 298 Kelvin and 1 atmosphere is known as a standard state, and arbitrarily assigned value for the enthalpy at standard state is 0. Now therefore let's talk a little bit more about standard state. So it can be a substance. So for elements we have decided. For other substances you can, like compound also. What is the standard state? The stable form of that element or compound at this temperature of 298 Kelvin and pressure of 1 atm is known as a standard state. So therefore the most stable form of element for elements, essentially why the stable form comes when the elements exist in solids. There are many forms. For example, oxygen, it exists in two forms, oxygen gas and ozone gas, and which is the stable form, it is oxygen gas at that condition 298 Kelvin and 1 atmosphere. Take the carbon, so it exists in several forms at 298 Kelvin and 1 atmosphere. It is a graphite, that is most stable form, therefore that was taken as a standard state. This is for elements. And for compounds, okay, we can take any compound, so no need to worry about the standard form for element. For compound, a compound is unique, and at what conditions? That at 298 Kelvin and 1 atmosphere, that is known as a standard state. So now let's take a state and which is called as a standard state. A gas, it has several states, but the state that has 1 atmosphere pressure at 298 Kelvin, that particular state is known as a standard state. Remaining all are non-standard states. And for liquid, we must take the pure liquid, not the impure liquid. Pure liquid should be a pure liquid, that at 1 atmosphere and 298 Kelvin. For the solid, we must take most stable form of the solids existing for that substance or that element at 298 Kelvin and 1 atmosphere. For solution, if you have a solution, another condition is that is 1 molar, 1 atm and 298 Kelvin, and those are known as a standard states for substances. Now what is the enthalpy of formation? This is very, very important. The formation, so energy associated with the formation of the substance. Enthalpy of formation. Enthalpy of formation. So we have already defined standard enthalpy. That is enthalpy of elements or compounds at standard state is known as a standard enthalpy, and we gave them some arbitrary values. Now, what is enthalpy of formation? The enthalpy of formation is denoted by delta HF naught, which is known as, the naught indicates standard, F indicates formation. This is standard enthalpy of formation. Enthalpy of formation. And what is this? Enthalpy change associated with the formation of 1 mole of substance from its constituent elements at standard state. All are the reactants are here constituent elements. The product is 1 mole of that compound at standard forms, and the energy associated with that formation of 1 mole of compound from its constituent elements is known as enthalpy of formation of that compound. And we already know that enthalpy of formation, standard enthalpy formation of constituent elements as per definition and arbitrary selection is 0. Therefore, now let's read the definition first. This is enthalpy change associated, or you can use the word accompanying, with the formation of, very important word, 1 mole of substance, 1 mole of compound from its constituent elements. So we are defining, fixing the quantity, that is 1 mole of the compound. Therefore, if I write this equation, H2 gas, which is an element, O2 gas, which is oxygen element, are combined to produce substance or compound water. And let's say this reaction is carried out to produce 2 moles of water from its constituent element. The energy changes associated, enthalpy changes associated is going to be 51.88 kilojoules. Therefore, do we call this 51.88 kilojoules as heat of formation of water? No, because here the water is formed in 2 moles. Therefore, as per the definition, the compound must formed in 1 mole. Therefore, to form 1 mole of water, we should use half mole of H2 gas plus half mole of oxygen gas. Now, this is going to be delta H, exactly half of this one. That's going to be 25.94 kilojoules. And why it is 25.94? We must understand that enthalpy is a state property, and also it is an extensive property. If we use the greater mass of reactants, we get greater mass of products and greater amount of heat changes. If we use the less mass, less amount of products will form and less amount of heat changes associated with that little amount. Therefore, the second equation is exactly indicating the formation of 1 mole of compound water from its constituent elements. Therefore, the enthalpy associated in this transformation is known as enthalpy of formation, standard enthalpy of formation of water. The moment I say standard enthalpy, that means the conditions are already fixed. The standard naught here indicates 1 atmosphere, 298 indicates temperature. So this is for today's class. In the next class, we will be going to learn standard enthalpy of formation of a compound is actually its enthalpy, standard enthalpy. So we will decide that point, and also we will also derive one more formula for delta H reaction, that is enthalpy of reaction, which is summation of bond energies of reactants minus summation of bond energies of products, that one. And also we will be going to do some problems regarding the heat of reactions, and also dependence of heat of reaction and temperature, which is known as a Kirchhoff equation, that also we will derive in next class. And this is for today's class. Thank you very much.